I will be your MC for this evening. We've got a super awesome event, really excited to share it with you. We'll have a talk by Wenbin Liu on black holes, and then an extended Q&A session between Wenbin, myself, and two other guests that are from the department. But before that, a couple of quick announcements. So the schedule for tonight, after a couple minutes of announcements, I'll introduce Wenbin. He'll speak for about 30 minutes, and then we'll immediately transition to our Q&A panel and be able to answer questions that you have about both the content of the talk, black holes, or anything really that you're wondering about astronomy or astrophysics or space science that we might be able to address. And that'll go on until 9 o'clock this evening, Pacific time. These events happen once a month. So if this is your first one, we have the archive on our YouTube channel going back for 5 years every month. So I encourage you to check those out. There's lots of really good content on there about all sorts of astronomy stuff. Our next one will be May, I forget the exact date, May 22nd, something like that. It'll be a Friday night. In addition to our stargazing lecture series, we also have Astronomy on Tap, which is a little less formal public event. These happen, traditionally they're held in a bar, but we aren't able to do that right now because of the pandemic. But we hold them over YouTube Live, and there are two 15-minute presentations that are given by scientists either from the department at Caltech, or since we've been doing them online, I can invite people from all around the country and the world to be guests. So our next one of those will be a week and a half from tonight, a week from this coming Monday, and the topics will be the first galaxies and the first stars in the universe, and the search for them and the implications of how they affected our lives today in astronomy and the world. And then we have an event 2 weeks after that that's all about telescopes. One existing telescope called SOFIA that is aboard a 747 jet that goes into the upper stratosphere every night and takes images of the cosmos, as well as a planned telescope that's planned to be built on the far side of the moon, a radio telescope. So obviously we don't have yet that built, but hopefully at some point it will be. So I encourage you guys to check those out. They're on the Caltech Astronomy website, or also on our YouTube channel. And they'll also, tonight is a bit of an experiment. We're streaming both to YouTube as well as to Facebook Live. So you can view it at that. Hopefully it'll work. I think it's streaming right now, but it'll be a bit of a challenge keeping track of all the comments and questions that we get from both platforms, but it's an experiment. So we'll see how it goes. I think those are all my announcements for now. Wenbin, would you like to come on here and I can introduce you? Excellent. Thanks for joining us tonight, Wenbin. I'm really excited to hear your presentation on black holes. Oh, you're muted. You can unmute too. Let's see. So if you go ahead and share your screen, perfect. Share your screen. So Dr. Wenbin Liu is a postdoctoral researcher in theoretical astrophysics at Caltech. He mainly uses pencil and paper calculations to study various explosive phenomena, including stellar explosions, double neutron star collisions, radio bursts of unknown origin from billions of light years away, and what happens when a star falls into a black hole. And outside of astronomy and space science, he also enjoys rock climbing and hiking, which is pretty awesome. So yeah, thanks for joining us, Wenbin. Do you want to take it away from there?
Yeah, thanks so much, Kamraj, and thanks so much for everybody who comes here to listen to the talk. So today I'm going to tell you a little bit about what astronomers know about black holes. We will focus on these three questions. This talk would not, has not much to do with the movie Interstellar. We will approach these questions from a scientific point of view. What do black holes look like? How do we observe them, right? And how do they form? How do we find them in the universe? Okay. So let me get started. So the history of black hole comes from Newton's thought experiment. So at that time, when Newton just discovered the gravity, mutual gravity from massive objects, he was thinking about the following experiment. Imagine you have the Earth and there's a little mountain here on the Earth. Our physicists, we think mountains are like this, simplified like this. So you have a cannonball. So you have a cannon. So the cannon shoots a cannonball in the forward direction. If the cannon is able to shoot, let's say at 1 kilometer per second, which is considered as a very, very fast speed at that time, it will fall somewhere on Earth, right? So Newton was imagining if you can shoot the cannonball at really fast speed, what will happen is that it can go farther and farther as you shoot faster and faster. By the time you shoot at this speed, 7.9 kilometers per second, this cannonball will not fall back on the Earth again. So you can see that it will go around the Earth. But you can keep shooting faster, right? Once you shoot, let's say 10 kilometers per second and 11.12 kilometers per second, that was Newton's number. And then this cannonball is gonna fly to infinity. It will not fall back to the Earth anymore. So that's called the escape speed. So once you can shoot something above the escape speed, that object will escape the Earth. So that's what we do nowadays. If you want to send a rover to the Mars, this is one of the latest ones. You have to shoot a rocket at a really, really high speed, close to the escape speed, such that it can get out of the Earth and land on Mars. And so a century after Newton's cannonball experiment, people were thinking in the extreme cases. So now you can imagine that this is the Earth, right? So you shoot something at 11.2 kilometers per second, it will escape to infinity. But if you just shoot at 10 kilometers per second, it will come back, right? Now imagine you have another object which has the same mass as the Earth, but it's a factor of 100 smaller than the Earth. So now the escape speed is a factor of 10 higher than there. You can see that you have to shoot 112 kilometers per second for the object to escape. Right now, imagine to the extreme case. These people are thinking about the extreme case where the Earth shrinks all the way to like a 1 centimeter size, which is like this size, like a rock on your palm. You have to shoot an object at the speed of light in order for that to escape the system. Anything less than that will fall back to this object. And that, people think, this object, even light cannot escape, then it will look black, right? There will be no light escaping from the system. That's what people call a black hole, right? So that's people's imagination. People at that time didn't know that this object it's so dense and so small, whether it can exist or not. So there is a concept related to the trapping of light from the object, which is called event horizon. So if you shoot light inside of this circle, it will not get out because you have to shoot at faster than speed of light, which is never possible. So light can only escape if it is emitted above this surface, which is called event horizon. Okay, so after many decades, after 200 years later, Einstein came, and Einstein's idea completely changed people's opinion on gravity, right? So gravity is no longer like a force, like a rope tied between two objects. Gravity, according to Einstein, is the space-time curvature, which I will later on explain in more detail. But you can imagine that this is the space-time, this is the fabric of the space-time, which is affected by anything that has mass. You have a mass, and anybody like a rock has a mass, and stars, these are different types of stars at different densities. The sun is not very dense compared to other compact stars. These are two other exotic stars, which I will never get to, but these are much denser than the sun, much denser than anything you can find on Earth. They are denser such that they curve the space-time fabric is curved more. To the extreme case is a black hole, which curves the space-time near it to the extent that it forms an event horizon, as we mentioned before, which will be a one-way membrane where things can only get in and nothing gets out. And one easily calculate the size of the event horizon, which the mass for a solar mass, this is for solar mass. For a 1 solar mass object, the size of the event horizon will be 3 kilometers. It's pretty small, it's smaller than the city size, but it has 1 solar mass in it. So, so the concept here is If you have mass is equivalent to energy. So this energy will serve as the purpose to curve the space-time fabric near it, and that's the gravity. Okay, so I'm telling you, this is the fabric of space-time near the Earth. So how do we know that the space-time is really curved, whether it's flat like shown here or it's curved? How do scientists actually test this idea, right? So as you will probably know, this idea of Einstein has been tested by many numerous experiments. I'll just tell you two of them, two of the most famous ones. The first one is light bending. You can imagine in a flat space-time, light will go as a straight line with no deviation from its original path. Whereas for a curved space-time, light will bend, right? And we can see this actually. So while we're standing on Earth, it's difficult to see how Earth bends light, and the moon is too small at the earliest time of people testing this. So people go to the sun. People go look at the stars behind the sun because the sun is very massive. And during a solar eclipse, right? Eddington, this person Eddington in 1919, 5 years after Einstein published his theory, going after a solar eclipse, right? Solar eclipse, so the sun is blocked by the moon, so you don't see the sunlight. You can see the stars behind the sun, and people can measure actually the star's position is shifted by just a little amount, exactly as Einstein predicted. Though this amount has shifted, and that's seen. So this came as one of the first proofs, first test of Einstein's general relativity. So there's another effect which I'll introduce, which is important for later discussion today, which is called time dilation. So this is to say, if you put two clocks, one clock on the Earth's surface, the other clock far away, they will tick at different rates. You can imagine for a flat space-time where you send a signal. Let's say on Earth, you beat a drum. Every 1 second, you beat the drum, boom, 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 right? This drum, let's say you send a light signal. It's like a drum. You send a light signal. So in a flat space-time, this periodic signal is gonna arrive at some faraway point at the same period, same time. But however, when the space-time is curved, this does not happen. What will actually happen and what's observed is that the beating pattern gets slower and slower once you get to larger distances, meaning that the frequency gets smaller, right? So that's called time dilation, and this time dilation was only observed. So this effect is really tiny. So it was observed in 1959 by these two people at Harvard. They're doing an experiment. So they have a tower. This tower is 22.6 meters tall, basically a building. So they send some radiation source, which is from a radioactive material. So they send a radiation source with known frequency. This is a photon with known frequency. So it travels all the way to the ceiling, and then you have a detector. You see whether the photon frequency has changed, right? And you can do the experiment backwards so that you get twice of the signal, right? So this amount of frequency shift is really tiny. It's only a few parts in 10 to the 15. And you can imagine, at Newton's time, nobody would have noticed this, right? And it's not only in 1959, this has been measured. And the end result is that if you sit on Earth over 100 years, like your lifetime, you actually gain 1 second. You age less by 1 second sitting on Earth than somebody far away. That's something quite cool. So another very important application is the GPS system that you are very familiar with. So you know that a clock sitting on Earth ticks slower than the clock on the satellite, which is above the Earth, right? And one can easily calculate using GR. Some scientists have calculated this, that every day, if a satellite is rotating around the Earth, every day, the clock on the satellite will be a little bit faster by about 50 microseconds every day. You might not think that's a big deal, but actually this corresponds to a light travel length about 10 miles a day. So if you do not correct for this, your GPS would be wrong after a day, would be tremendously wrong. You might think you're in LA, but actually you're in Pasadena. So it's a different place. So this, so I quoted here, so every ordinary user of GPS, actually, you are actually testing Einstein's GR every single day, every single time you use your GPS system, okay? So let's go to the extreme case because we're interested in black hole. So if the black hole is so massive, so dense, that it actually curves the space-time near it to the extreme. So here is a scientist. So scientists think about black holes in this way, where you can, from Einstein's general relativity. So this is the actually you can imagine this, an astronaut, let's say of 1 meter, 1.5 meter tall astronaut. If you put the astronaut here somewhere far away from a black hole, this is the amount of space it's going to take. This is the delta R, which is the space that is taken, but this delta R does not equal to the actual height of the astronaut, which is delta S. Delta S can be larger than delta R. So in the reverse side, if you look at the astronaut when it's very, very close to the black hole, it actually looks much, much shorter than the astronaut really is. So this is in contrast with people, some artist impression people typically draw it in this way, which is incorrect from a scientific point of view. The astronaut should look shorter and shorter as you approach the black hole instead of being stretched. So another thing which I already mentioned is the time dilation, right? The time dilation near a black hole gets so extreme because mu, this factor mu, which is the ratio between these two, gets so tiny. It's very, very, very small, such that the clock, if you put a clock just very, very close to the black hole, the clock basically does not tick from a faraway point of view. The clock comes to a standstill. Okay. So another very cool thing is that, let's say I have made this plot this afternoon. So if you imagine there is a black hole, the black hole has a radius of 1. So this is in units of this horizon, event horizon radius, which we call RS, which is size of an event horizon. So if you put a light bulb, right, a light bulb, you can put the light bulb anywhere you want, but not inside the event horizon. Let's say you put it at 1.1 event horizon radius right here. So right, the light bulb emits light in all directions, right? So only a tiny fraction of the light can escape the black hole, whereas the majority is captured. If you put it at 1.1 times the size of the horizon, most of 85% of light is captured, whereas only 15% is escaping. But if you put it somewhat far away at 2.2, the size of the horizon, only 25% is swallowed, whereas 75% escapes. So that's the light capturing. That's just the space-time curvature that made light capture possible by the black hole, right? So here are what black holes look like. So now you have a good idea on what black holes should look like. They can swallow light. They may bend light, and time ticks slower near a black hole than farther away. So now let's talk about how do black holes form. So let's go back to the Earth, right? We know that the Earth has gravity. Everything is being pulled towards the center of the Earth. So why doesn't the Earth collapse, right? Because there's tendency to move towards the center of the Earth. So that's because there is a pressure in the Earth interior. This can be seen if you go to Hawaii, if you go to Yellowstone, you see that the Earth interior has very hot material, which has a strong pressure, which resists this gravity force, right? Actually, on the surface of Earth, this is exactly balanced. These two forces are exactly balanced so that the Earth does not neither shrink or expand, right? So the same thing happened to a star, right? Let's say if you take the sun or other more massive stars, you have gravity, which is due to the mass of the star. You have pressure. The pressure is supplied by heat. So the heat actually comes from nuclear fusion reactions, which comes from hydrogen, which collides with each other, and then that generates energy while they fuse and become heavier and heavier elements. So it is a nuclear fusion reaction, goes on and on, all the way until a certain very heavy, very massive nuclei where you no longer get energy out of the fusion reaction anymore. And that is the point where the sun or any other star run out of fuel. And at that time, it should collapse, right? So the collapsing, there are a couple of options that we know that it can collapse to. There are two other options, which I kind of mentioned before. There is a white dwarf or neutron star. These are so again, supported by pressure. There are quantum mechanical pressure that can support them from further collapsing. Whereas for even more massive stars, so as a star gets more and more massive, this has a tendency of going towards the black hole scenario. So here for the other cases, there are pressure, right? So which can resist the star from collapsing into a black hole, right? So it took all the way until 1935 and 1939 for people to realize the following property of general relativity. So you have gravity, right? There's a very dense object which has very strong gravity, and it requires a very strong pressure to support it from collapsing, right? And what Einstein's general relativity tells is that pressure is also a source of energy, which is also a source of mass, right? So as you increase pressure, you unavoidably increase the mass or the energy of the system, which curves the space-time more, right? So unavoidably, once you increase the gravity to some level, which there's a maximum amount of gravity you can have, that the system will unavoidably collapse to a black hole. So that's what Thoma and Oppenheimer and Volkov found. So they found that when the mass of an object, so if there is no other energy supply, if a mass of an object is more than about 3 solar mass, this mass is named after these people, that it will unavoidably collapse to a black hole. So that lays the foundation that we know that massive stars should be making black holes in the universe, right? So, okay, so how do we find these black holes? As we already know, we know the properties of black holes, so it's pretty straightforward. What should we look for, right? So let's go look at those objects that are more than 3 solar masses. They're non-luminous, right? Black holes are dark, right? Or we can look, alternatively, we can look for things that are being swallowed by the event horizon, which is the point of no return, right? You can only go into the horizon, but nothing comes out, right? Or we can go look for gravitational waves. That's the ripples of the space-time fabric. If a black hole is moving very rapidly, then that excites gravitational waves, which can propagate to large distances. So let's look at each of these options and see if people have succeeded or not, right? So the first case is looking at, let's say there is a binary system here, but we don't see this object, right? This object is dark, but we know its existence because we see the star, right? We see the starlight. So the star periodically orbits this dark object, and this orbital velocity of the star causes the so-called Doppler effect. So when the star approaches you, it looks a little bluer, and when the star it recedes from you, it looks a little redder. This can be tell from spectral lines from the stars. So that people actually measure for many systems. This is one of the famous systems where people measure this so-called radial velocity. So this star is orbiting around a dark object at hundreds of kilometers per second. And from that velocity, this is as a function of time, from that velocity, people can infer that the mass of this object, this unseen object, is more than 6.3 solar masses. So we know that it's most likely a black hole because it's more than the TOV mass, right? So there are other scenarios where we know that there is gas or just material mass is fed to the black hole, where it actually spiral and get all the way to very, very close to the black hole, where it gets so hot, it shines in the X-ray band. So our X-ray telescopes can measure, again, through Doppler effects, can measure the motion of the hot gas near this object. And the motion is such that it's moving near the speed of light. So we know that the material must be very, very close to the horizon, to the event horizon. So we know that these objects are also most likely black holes. This can be seen from a stellar binary system or from center of galaxies where there is a dark object sucking matter from the nearby environment. Okay, so the more extreme case is that we go to the center of the Milky Way. If you go to the center of Milky Way, you zoom into the very, very center of Milky Way, you see those stars. You can see the stars are moving. The stars, obviously, you can see that they're apparently moving around some dark objects, right? There seems to be a dark mass that's attracting these stars. And this is from the The earlier one was from the German group from Reinhard Genzel's group, and they utilized the European very large telescopes in Chile. And another independent group, which is from the US, led by Andrea Guess from UCLA. And people, this is from the Keck Observatory in Hawaii. People, again, they can measure the orbit of these stars, and all the orbits point to the same conclusion, that they seem to be orbiting around the same center of mass, which is shown by a star over here. And by those orbits, people can measure, let's say if you pick one of these stars, this is called S002, one of the nearest stars, it is orbiting around this object. And this position of this object can be measured by other means as well, shown in the red dots over here. We give it a name, it's Sagittarius star. So by measuring the orbit of this star, it's a 16-year orbit. You can imagine how much energy, how much effort astronomers have put into this orbit. And people monitor the entire orbit of this system, and they come up with the mass of this object. It came out to be about 4 million solar masses. And from this orbit, we know that its size, the size of this object, must be less than about 10 AU. 1 AU is the distance between the Earth and the Sun. It's very, very compact. And this scenario actually rules out nearly all the alternative astrophysical scenarios. And people came to the conclusion that it's most likely a black hole. This is a supermassive black hole because of the high mass. So another way of even more astonishing way to look at the system is you look at a nearby galaxy called M87. So here's M87 it's an elliptical galaxy, and where it shoots out a jet of material. So this is an image in the radio band. So if you zoom in to the innermost region of this jet, this is what you see. You can see material has been launched away from this point source all the way at very, very high speed. And if you zoom in further, so this further zoom in is enabled by an Earth-sized telescope shown over here. These are radio stations. All the radio telescopes are combined together to make this image such that you can have the enormous resolving power. So they were able to resolve such a tiny 0.01 light year of size at a great distance from the Milky Way. And from this, people can measure the mass of this object. It turns out to be 6 billion solar masses. And here you can see that the light is missing from interior, and there is a ring of light, right? That's exactly what a black hole would do, because the black hole can capture light within a certain range, and the size and this ring is called light ring. And then this is compared to the solar system. You can see the solar system is tiny compared to this black hole. This black hole is so big that it encompasses the entire solar system, more than the solar system. So another way that we know the existence of black hole is by observing gravitational waves from two black holes. So this is an example of two black holes that when they get really, really close to each other, this is the size of an event horizon for each of them. And this is shown in color is the curvature of the space-time ripple, is the space-time fabric near the black holes while they move through the space-time, and they excite these ripples, so you can see right now the curvature is extremely large near a black hole. This is the black hole event horizon. You can see the dark here, the dark region here, that's the event horizon. Right now the event horizon is dynamical because the black hole hasn't settled down to a steady state. And here is the ripple that is detected by our laser interferometer gravitational wave observatory here in the US. These are composed with 2 arms of 4-kilometer arms. When the ripples come to the Earth, the arm length changes by a little bit. It changes by only 1 part in 10 to the 21. It's a very, very small shift, but we're able to detect it even though. So now with these gravitational detectors, so we have detected many such black hole mergers. So here shown in blue are these ones that we have detected. There are about 40 to 50 of these ones. You can see that each of them have 2 little black holes merging into a more massive black holes. And so this significantly expanded our view on before the gravitational wave astronomy. We only know these purple black holes. These are from binary motion. And with the gravitational wave observatory, so we see there are lots of black holes in the universe. So these black holes, we believe they are formed from stellar collapse. These are from massive stars. But we don't know whether black holes can exist at larger distances. There is a hint from gravitational wave observation that there is a lack of these objects, but it's not certain yet. So here is my final slide. So here's a summary of what we have talked about. So we know, so here's the mass in this axis. I'm showing the mass of these objects in units of solar masses. So we have no black holes in stellar binary systems. Those are close to about 10 solar masses. Those are in binary systems. And we know some black holes from something like 10 to 100 solar masses from merging system measured by our gravitational wave detectors. We also know there are black holes at the center of galaxies. Two good examples are the one in the center of the Milky Way, the other one in the center of M87 galaxy. So those black holes are so-called supermassive black holes. Their masses are between something like 1 million to 10 billion solar masses. So there you can see that there are still gaps in our understanding of the entire mass spectrum. We don't know whether there are these mini black holes less than about 3 solar masses, although our stellar evolution picture do not predict these things to exist. And on the other hand, we don't know whether there are like there's a hypermassive black holes more than 10 billion solar masses. And somewhere in between, these are guessed to be intermediate mass black holes. We also don't know if they exist or not. So there are these frontiers in our astronomical searches in the future that we're gonna look for these black holes. Yeah, so here is my presentation. Thanks so much for listening.
Thank you, Wenbin. That was excellent. That was great. Let's see. I'm gonna stop your sharing. Excellent. So, audience members, we are going to immediately transition to a Q&A panel consisting of Wenbin, myself, and 2 other guests. Nikita and Jesse, can you guys turn your cameras back on? Welcome, ladies. Excellent. Okay, so audience members, many of you asked questions throughout Wenbin's talk. Excellent. We've noted them down. There's a lot of questions between both YouTube as well as Facebook Live. There's lots of different people asking things, but we'll try and address as many as we can. Feel free to continue to ask questions in your respective platform in the little chat section down at the bottom of the screen, and we will try and address them here. But before we get started with the Q&A panel, I want to introduce all the speakers on the Q&A panel. So Nikita Kamraj, would you like to introduce yourself and what sort of science you work on?
Sure. Thanks, Cameron. So I'm Nikita. I'm a graduate student at Caltech in the astronomy department. Actually, my final year right now, and I also study supermassive black holes. So I study accreting supermassive black holes called Active Galactic Nuclei, or AGN. And specifically, I use X-ray telescopes to study these objects, trying to use X-ray spectroscopy to elucidate information about the geometry and nature of the material that's falling into these supermassive black holes, and figure out how these supermassive black hole systems accrete and behave. And as an aside, I also am on campus involved in a lot of student advocacy, advocating for minoritized genders and promoting gender equity in STEM fields. And I also love Japanese culture. So if you have questions about any of those things, feel free to ask.
Awesome. And our other guest is Dr. Jesse Christensen, who has a really awesome background here with like a nebula and oh yes.
Just sneaking some Doctor Who in there.
Yeah, excellent. Go ahead and introduce yourself.
Hi, everybody. I'm Jessie Christensen. I'm a research scientist at the NASA Exoplanet Science Institute, which is actually at IPAC on the Caltech campus. My research is I search for and characterize and catalog extrasolar planets, so planets around other stars. And that's also my day job, is to be the keeper of the exoplanet archive. So how NASA keeps track of all of the planets that we found and all the properties of them. And I used to have hobbies, but now I have small children. So that's what I do in my spare time.
I imagine, especially so during the pandemic, it probably keeps busy with all the childcare stuff.
Yes.
Okay, great. So yeah, now, oh, and I guess I'm me. I'm Dr. Cameron Hummels. I do research in computational modeling of how galaxies form and evolve over the whole duration of the universe since just after the Big Bang, and try and understand, yeah, how these things form, why certain galaxies are the way they are and are different from, let's say, our Milky Way galaxy, and what processes govern that and what makes them differ in their overall evolution. So I'm happy to answer questions on that, or help answer questions on whatever people have. We have lots of questions that people have already asked. Here's one that's relevant to the talk about primordial black holes. Are there real primordial black holes? Do we have evidence for black holes that formed not just from stellar collapse, but that somehow were formed at the beginning of the universe from some unknown process? Wenbin, do you want to take this one?
Yeah, let me answer this question. It's a nice question that obviously scientists have thought a lot about this question. And the answer is there could be, but it's not in the majority of the mass. Only a very, very small fraction of the total mass of the universe could be composed of these primordial black holes, because we know should have, right? They should accrete matter from nearby environment where the matter, well, just infalling matter will emit light in some sort of light that we can see. There are other effects that these primordial black holes would have. They can perturb the orbit of the outer planets, the outer comets in the solar system, and some of the other effects. There are many other effects. They evaporate. The very, very tiny black holes, they will evaporate. So all this physics that we can combine in total, such that is about less than about a if the primordial black holes only could be zero.
You're cutting out a little bit. You're keeping us all in suspense, but I think most of it came through there. Okay. So bottom line, we don't yet have evidence for primordial black holes, but they may exist. Some are consistent with our models. Uh-oh, I hope Wenbin didn't freeze entirely. Oh, I see signs of movement.
Yeah, and I would just add to that,
Okay,
that primordial black holes are also like one of the leading ideas for how we form supermassive black holes in the very, very early universe. How we get, these very distant, what we called high redshift quasars that have masses of billions of solar masses formed so early on in the universe. The idea that they were formed from primordial black holes is one such popular theory.
Excellent. Yes, absolutely. Okay. Let's see. Lots of questions here. Eventually, over billions of years, will every star over 5 solar masses become a black hole, based on the thing that you presented, Wenbin? Oh no.
That's a great question. So, am I freezing again? I think I should.
We can hear you okay. Your video is a little choppy, but we can hear you okay.
I see. Yeah. So the end is pretty much every single star is uncertain. About 20 solar masses, they would end up collapsing, form a black hole. Between 5 and 8, they form white dwarf stars, and between 8 and 20, they form neutron stars instead of black holes, because they're not dense enough. Neutron stars can still have pressure support. Roughly about 20, you can no longer have enough pressure support at the core of the star, such that it will form a black hole.
Okay, cool. So different ranges there in terms of what the eventual behavior will be. either white dwarf, neutron star, or black hole being over 20. Just to confirm, because he was chopping out a little bit in his audio, but great. Okay, here's an interesting one. So if a you were talking about time dilation a lot, and how time slows down or speeds up based on the trajectory you take through space time and whether or not you come close to a massive system or how fast you're traveling. So the question that's asked by Zapfan is, if a GPS receiver flies on an airplane from Los Angeles to Sydney, which is like 15 hours at well, they're proposing 15 hours at 1,000 kilometers per hour, which is pretty fast. How far off does it get over the course of that flight? How far off? I guess the question is maybe how far off is their time, their clocks relative to when they started and relative to what it should be because of relativity.
So let me answer the question. I'm still doing the computation. There's exactly how this can be calculated is very simple. So first you have to consider that the GPS receiver, this person is flying. So there is a motion, right? Anybody in motion, its clock actually is slower. So that is a negative effect. Another positive effect, which is more important, is the general relativistic effect, which actually, because you're slightly farther away from the Earth's center than on the ground, your clock actually ticks slower. So these two effects add together. The net effect is that your clock actually ticks slightly. So the second effect is that your clock ticks faster. So the net effect is that that your clock ticks slightly faster, not by much. So the amount that you tick faster at is given by the following. So you have to, these are the two, this is the factor that you do. So there is a factor that's the kind of a few kilometers per second divided by the speed of light and then squared. That's the fractional, that's the fraction. So every second you take, that's the fraction. And then another factor is the ratio between the distance to the ground to the radius of the Earth. So these two factors multiply together and then multiply by your 15 hours. That's what it is. So you can do that number. I may not be able to do that number right now, but you multiply those together, that's what you get. You may get a tiny number that your clock doesn't even recognize.
Okay, there, sorry. Okay, so let's switch gears a little bit. There was a question about our solar system that might be appropriate for our exoplanet specialist here. Is our solar system unique?
Yes, that is a great question. And it's something we've been trying to find out the answer to for a long time. Literally thousands of years, the Greek philosophers used to talk about, like, is the Earth unique or is it plural? What I can say is that what we have found so far does not look like our solar system. So the kinds of planets we found so far are typically big planets like Jupiter and Saturn that are very close to their star, much closer than the Earth, which is super interesting already, these solar systems that have these gas giants that are really hot. Or we find these like strings of what we call super Earths. So those are planets like 2 to 4 times the size of the Earth that are kind of all very compactly nested in together in these resonant chains. Yeah, one of the things we found is that solar systems seem to have planets of the same size in them. So, it's all super Earths or all Neptune-sized things or all gas giants. Our solar system, in that sense, actually seems to be unique because we have this mix of things, right? We have these small rocky planets close to the star and these giants, these gas giants and ice giants further out. And that seems to be unusual, which has all sorts of really interesting implications for life, right? Like, how important is it that we have a Jupiter-sized planet, because Jupiter did a bunch in terms of like shepherding comets towards us to deliver water, shepherding comets towards us to murder the dinosaurs. There's lots of reasons why having Jupiter is good and bad. So we don't know if our solar system is unique. It doesn't seem like it's the most common kind of arrangement of planets. It seems like it might be a bit unusual, but we haven't got the sensitivity yet to say that it's truly unique.
Okay, that's cool. Well, yeah, it seems like the rate at which we're detecting new exoplanetary systems, maybe we'll be able to have more of a clarification on that at some point in the near future.
Yeah, so there's a new telescope that NASA is launching in the second half of this decade called Roman, the Nancy Grace Roman Space Telescope. And one of the things it's going to do as part of its sky survey is to search for planets towards the galactic bulge, the center of our galaxy. And the method that it's using, microlensing, is actually more sensitive to solar systems like ours than the methods we've been able to use so far from the ground. Other ways of finding planets. So we're hoping that now that we've basically started to really understand inner solar systems, like out to where Earth is, we've got a really good census of the types of planets and the sizes of planets and the distributions of planets close to the star. We're hoping with Roman that we'll be able to complete that census and get the second half of the equation, right? Like what's outside, what's Earth and out? Like what does that look like around other stars? Then we can start to have this like holistic picture of what do solar systems truly look like around other stars, which we don't know yet, but it's so exciting.
It's super exciting. Absolutely. Lots more black hole questions. Stephen Schreier asks, is it safe to say a space probe approaching a black hole would be incinerated before reaching the event horizon of the black hole?
I'm not an English speaker. Is incinerated destroyed?
Incinerated just means burns up. Like,
oh, okay.
Like gets so hot that it burns up.
Yes, I see. Yes. The answer is no. The spacecraft, as the space probe, as long as it's very, very tiny, it actually does not get heated up. The only thing that happens to the spacecraft is that it accelerates towards the black hole. It accelerates to near the speed of light before plunging into the event horizon. Of course, when the spacecraft is big enough, there will be tidal forces. One side of the spacecraft would feel different gravity than the other side. So the spacecraft would be crushed, would be tidally torn apart. But that does not generate much of a heat. It will not burn up. It will be like shredded into pieces, to tiny pieces, and all the pieces will later on fall into the black hole.
Great explanation. Sorry, I'm trying to comb through all the questions that are coming through. Let's see. If string theory is verified, which is a big if, but if string theory is verified, Catalina asks this, could we speak of a unification of the theory of relativity with the quantum world? Because I know that's, people often know that people are looking for grand unification theories that unite all the known forces in the universe, and would string theory adequately do that? I guess is the question.
Yeah, so let me answer the question. So the question is a very great one. So people always, astrophysicists, including all the physicists, have been hoping to have a unified theory between general relativity, which is not quantum. All the things are smooth and continuous in the general relativistic language, whereas in quantum language, everything is discrete, right? You have quantas, different. So the unification would only come in a very, very, very distant future. Right now, we don't know if string theory is correct. We cannot test it. So the only deviation that people can think of from away from general relativity is a tiny, tiny amount. So this amount is about 10 to the minus 33 centimeters. This tiny, tiny amount of, if we can really probe to that length scale, which is called the Planck scale, we can try to unify gravity and the quantum mechanics, which would call quantum gravity. Before we ever get to that kind of tiny, tiny length scale near a black hole, we cannot really test or say right or wrong. So that's what I would say the string theorists are trying to look for new ways to probe that length scale, that tiny length scale. We have to be extremely creative to think about an experiment that can probe to that tiny scale. At this moment, our experiments are far, far, far behind, far away from really getting to that scale and test it. It's unclear whether we will ever get to that point and what will happen, whether quantum gravity would behave like what the string theorists are saying. It may be something else.
Great. This question, I think, is in response to some of the stuff that Nikita was saying earlier, and that is, how massive are the black holes that we've been able to observe in the universe? Because you mentioned, some of these high redshift quasars, these high redshift black holes that are supermassive. So how massive do these things get? Do you know?
Yeah, so Wenbin had like a really nice final slide in his presentation, which kind of summarizes the kind of full mass range of black holes that we've observed in the universe through various techniques. And to kind of just summarize that again, we kind of right now have like two different regimes of black hole masses or types. Those that are like the stellar mass black hole range, which are formed from the explosions of massive stars, and these black holes tend to have masses in the range of a few to, at the upper end, a couple hundred solar masses. And then we have the other extreme, the kind of black holes that I study, which are supermassive. They reside at the centers of galaxies, and they have, at the very low end, masses of about 1 million solar masses, all the way up to greater than 1 billion solar masses. And we believe the formation pathways are well understood for the stellar mass black holes, and it's still a bit of an enigma how you grow the supermassive black holes to such high masses. And then there's, of course, what's the in-between? Do we see black holes in this intermediary range between stellar mass and supermassive black holes? And that has been a really active area of research, is, do intermediate mass black holes exist? And if so, how can we form them? And where do they fit into the paradigm of black hole evolution? So this is, an effort on part by gravitational wave observatories that are, finding mergers of black holes that are really pushing the upper end of this black hole mass scale. And there's also evidence from, studying the stellar orbits of stars, around the center of our own galaxy in the Milky Way, suggests that they're orbiting objects that appear to be intermediate black hole sizes, so about 10 to the 5 solar masses. However, there hasn't been substantial concrete, like smoking gun evidence that such intermediary black holes exist. But if they do, then that would really elucidate to us how we can bridge the gap from these stellar mass black holes to forming these supermassive black hole systems.
So
of course, the supermassive black holes can be studied at various wavelengths and are very bright, a lot of them. And so so we can study them across the electromagnetic spectrum. And the stellar mass black holes are similar. We often find them in binary systems, and the mergers of stellar mass type black holes can emit gravitational waves, as do supermassive black hole binary pairs. So those are just some of the techniques that we use to detect black holes.
So when you say intermediate mass black holes, what range, just to make it clear for our audience, because we're talking about stellar mass, so stars make like, a few solar masses black holes, whereas the supermassive ones, as we talked about before, are like millions or billions of solar masses, of times the mass of the sun. So intermediate is just the range in between those?
Yeah, around 100,000 solar masses. Though on the low end, it can be as low as maybe 10,000 solar masses. And then on the high end are, just approaching 1 million solar mass black hole. So there are some very low luminosity active galactic nuclei that have very low black hole masses. And there are some very low supermassive black holes that are almost on the intermediate black hole mass range, but yeah, the lower end would be about 10,000 or even a couple thousand solar masses. It's quite difficult to even if you think about the stellar mass function, which if you look at the graph, the number of stars that you see at higher masses drops the higher you go up in mass. That's what we call a stellar mass function. And so it's harder to produce black stars and thus black holes born from those stars at the very upper end of that mass scale.
Great. Thank you, Nikita. So here's a question that kind of collaborates all of our specialties together, and that is the search for Planet 9 in the outer solar system has included the hypothesis of a small black hole. Instead of like that Planet 9 is actually a black hole. It's not a planet, and that's why it's so difficult to see. Does anyone care to offer a comment on this? I have opinions on this, but I'll hold off and let you guys say.
I mean, there's 4 scientists on the call, so there's at least 6 opinions, right? Yeah, so I mean, to give folks who don't have more background, the reason people think there might be something like a Planet 9 is if you look in a certain part of the sky, it looks like there's a cloud of objects, the Kuiper belt. It looks like some of those objects are lined up in a certain way, that their orbits have all kind of been torqued in a certain way so that they're kind of all lined up. And that observation itself is being debated amongst the astronomers, whether that's a real overdensity of orbits that are elongated this way. But starting from the assumption that it's real, one of the ways you could cause this kind of grouping of objects of them all to kind of be lined up is if you had something that was massive outside of their orbit, kind of like shepherding them all. So this idea is that there's something past Pluto that's something like a super Earth. So I mentioned super Earths earlier. And this was one of these new types of planets we found when we started finding exoplanets that are bigger than Earth, but smaller than Neptune. And in our solar system, there's a gap. There's the little rocky planets, and then there's the gas giants, but there's not really anything in between. So it was really kind of a surprise when we went out into the galaxy and found all these planets that are in between. That's a whole new thing. So this hypothesis is that there's something like a super Earth or a mini Neptune out past Pluto that's shepherding all these objects together. Now, to be that massive and to be a black hole, that's the part I can't speak to because I'm not a black hole physicist. I'm going to point to the people on the bottom of my Hollywood squares here. But there is this idea that there's something more massive in the outer solar system causing these objects to be lined up. Whether you can have an 8 Earth mass black hole is not my specialty.
Black hole specialists, would you care to comment on the possibility that the outer solar system harbors a low mass black hole?
I personally think it's highly unlikely that we haven't had any other evidence of the existence of such black holes. Right now, it's a very speculative, it's a possibility, but it has a very, very low probability of being true. Because otherwise, if that were true, then there could be other effects of such mini black holes existing. If they exist in the solar system, they might exist in other systems in the entire universe, everywhere else, just statistically, and they may have other effects. We should look at other possible effects that they may have, just given the number density, how many per solar system that we would have, and we should look at those effects. I would say there could be some other effects that it's violating some observational facts or something. I personally haven't studied that, but I think it's highly unlikely, and we don't know how those objects might form.
I was going to say, how do you make one that small? Could it be like an evaporating one? You mentioned evaporating ones earlier.
So those ones will not evaporate. Yeah, it turns out. Yeah, so the evaporation time, one thing to keep in mind, to remember in the audience, is very interesting. So if you have a black hole of a mass of like a mountain, there are many, many mountains, like some small mountains. So it's something like 10 to the 14 grams, if you want a number. So if a black hole is more massive, its evaporation time is very long. as mass. So if you have mass that's 100 times more than 10 to the 14 gram, then its evaporation time is 1,000 times the age of the universe. So it would not evaporate. Those ones like super Earth, those they would not evaporate. They would, if they do exist, they would exist forever, basically.
Okay, so 1,000 times the age of the universe, or approximately the length of this pandemic so far.
That's right.
Yeah.
Yeah, so I think all the suggestions of it being a black hole means that it has to be a primordial black hole that formed out there, that isn't associated with stellar production or isn't associated with any other like production mechanism that we really understand, which also suggests that not only do we not have observational evidence for other objects being like that in other places in the universe, we don't even really know that such a thing, we don't have any evidence that you could even form one of these by any mechanism. So I think it's unlikely. It's possible, but like lots of things are possible and super unlikely.
Yeah, I agree with Wenbin's points. I also don't think that is of all the possible theories out there that it's one of the more least likely to me. Like Wenbin was mentioning, there would be other effects of such a black hole that observationally we should be able to see. Like, you know, when you have black holes, as Wenbin was talking about, they distort space-time. Would we see some kind of microlensing effect from that? And the fact that even in just a previous stargazing lecture talk a few weeks ago, astronomers tend to have this sort of almost bad habit of coming up with very esoteric theories that is very difficult to observationally verify, when Occam's razor might be more appropriate. So.
Agreed. Very good point. That was I've been keeping that in my mind since we had the lecture by Shri a month ago about unnecessary theoretical constructs that aren't necessarily evidence-based, and trying to not just invoke them all the time. Okay, so Penelope, age 9, asks, what happens to the radiation that leaves a black hole? Where does it go to? Do we know what happens to it after it leaves the black hole? Or I guess leaves the accretion disk of the black hole, perhaps? Or once it gets absorbed into the black hole? I'll leave it to the black hole specialist to respond to this.
That's a great question. So once radiation leaves the black hole, so if there is nothing nearby, just the black hole and vacuum means there is nothing around the black hole, the radiation would just keep traveling all the way to kind of the end of the universe. So there's nothing stopping it. Whereas in the real universe, where we have gas, we have material, we have matter near every single black hole, there is matter. So eventually either this amount of radiation gets traveled to very far distance, and eventually most likely it will get kind of absorbed or scattered or kind of get changed into other forms of radiation by the matter. It's not that some of the light would not, it depends on the wavelength of the light. Some of the light can stay for a very, very long time. When you actually get to the size of the universe, then the expansion of the universe kicks in. Then the light, the wavelength can get longer and longer. It's no longer the initial light that you emit from near the black hole, though. It will get deformed by all the other effects that are existing in the vicinity or very large distances from the black hole.
Is
so
there
that would be
black
the
hole
fate.
radiation passing through Penelope right now?
Yes, there is not from the black hole. The black holes, some black holes, the tiniest black holes, they do radiate. This is what Stephen Hawking predicted, and people believe that it's still true. But the most massive black holes, they basically do not radiate. Their radiation is so weak. But there could be matter that are near the black holes. The matter can radiate, can emit light. So the light emitted from those matter, they can, they're in different forms. They're in radio waves, infrared light, visible light, gamma rays, and X-rays. Some of the radio waves, they can easily penetrate through your body and penetrate through buildings and all the materials. So yeah, there are radio waves who could be from some black hole, some material near a black hole in a distant universe where that is penetrating through my body right now. That's what's happening.
Yeah, like Wenbin was mentioning, how the radiation from a black hole interacts with the surrounding medium has important effects on like the galaxy as a whole. So Cameron can expand on this a bit, but particularly supermassive black holes, the radiation that they emit plays an important role in regulating feedback in galaxies. So light, while it's not a particle, it still has a pressure that it can exert on particles. And so there's this thing called radiation-driven feedback, and it plays a part in essentially not making the galaxies become too cool and injecting energy essentially back into the galaxy. And this is a very important process for regulating the evolution of galaxies as a whole. And particularly when we think about matter falling into a black hole and then the radiation given off, there's also like a feedback loop going on there, particularly when we talk about, for example, the quasars, which are these supermassive black holes that we see, that we don't see it shine light in certain phases when there's a lot of matter just falling in, and we say that the black hole is essentially obscured. But then once enough matter is accreted and that begins to produce a lot of radiation from the accretion disk, then we say that the quasar has turned on, and essentially radiation-driven feedback blows away all that obscuring matter, and it's like the quasar has entered the active phase, and we can visibly see the accretion disk and the light that's emitted from the black hole. So the way that radiation interacts with matter, it's almost like a symbiotic relationship between radiation and matter.
That's right. Sorry, I was trying to find a nice graphic to show that was illustrating this. But honestly, the background that you have, Nikita, kind of describes a lot of what, yeah, exactly. So is that an accretion disk around a black hole and then a jet that's erupting?
Yeah.
Well,
yeah.
Okay.
So I forgot to add that the radiation obviously interacts with the particles and the matter, and also is intertwined with the magnetic fields of the system. And so in certain circumstances, this can lead to jets being launched, which is kind of what my background image shows. And this is a major way in which energy is dumped into the galaxy in the kind of feedback cycle that I'm telling you about. And yeah, so I mean, this image is like of the accretion. So I'm trying to find my, I don't know if my finger can, okay. But yeah, this is a black hole and then the accretion disk. And what I study specifically is the X-ray radiation, which is produced in like this hot cloud of plasma called a corona. Very apt for our times, but not the people killing kind. And this produces the X-ray radiation that we see, and it can also power the jets that are launched out of a black hole.
And so related to that, there was a new paper put out this week by the Event Horizon Telescope group, the group that you are probably familiar with because they made the first image of a black hole that was released, what, like a year ago or so. But they put out a new paper, and this is totally relevant to this discussion. I'm not just like pulling this out of my ear here. They put out this really this cool paper that has a beautiful illustration of the black hole at the center of this neighboring galaxy, M87. Both the canonical image that you're now familiar with of the black hole as it looks in radio, but also what it looks like in different wavelengths of light, spanning from the visible wavelengths that we see, so something with an image taken with the Hubble Space Telescope at the same time that canonical picture was taken, as well as pictures of what the larger structure around the black hole, and you can see that jet of material that's coming out from matter being accreted slowly onto the black hole and then erupting in these explosions. And so I will show that really quickly here because it's also just a really cool image. Can you guys see that okay? So here's the image that everybody is familiar with, probably, that the Event Horizon Telescope folks put out recently. So that's like the super zoomed in view of the black hole in the center of the galaxy. And spanning from the left side to the right side of the screen here, it should be showing long wavelengths to short wavelengths, or low energies like radio to visible wavelengths of light, like you can see with your eyes, to then X-rays and gamma rays on the right side. And as you go through each of these images, this is like zoomed out. So this is 1,000 light years across. This image is 1,000 light years across. And then this is zoomed in and only 25 light years across. And then this is only 2 light years across. And it keeps going down, and you zoom in until you're only, 1/100th of a light year across, a few light days across. But then similarly, this is about 2,000 light years. This is about 1,000 light years. But you can see this jet of material, like the jet behind Nikita in her image, of stuff that's getting shot out of the core of the black hole, and along this really, it's traveling at near the speed of light, this material, and so it can penetrate quite a far ways out from the launch site. And then here's the X-ray, and you can see those jets. I just think this is an amazing image, and I haven't read the paper yet, and I haven't fully processed everything, but it seemed relevant for the discussion that we were having here. Okay. Let's see. Other questions? Why, Mohammed Soliman asks, why do photons get attracted by a black hole's pull, since they're not particles? They're photons, they're light rays. Does energy also get pulled by gravity?
Okay, let me answer the question. So a photon, the nature of a photon is kind of debated. You can say it's a particle, you can say it's a wave, it's like a piece of a wave. The fundamental reason why a photon gets curved and it gets attracted by black hole's pull is because of the curvature of the space-time. It's not, so since Einstein's time, people no longer think like gravities are like two rope tying two objects together. It's so the black hole curves the space-time near it. So the space-time is curved such so the photon would move along the straightest line in the locally straightest line possible, and the photon in the local patch of the space-time fabric, it does not know what is the global picture of the system. It just follows its local path, right? It's like you're walking on a hill, right? You only know you want to walk downhill. Let's say you don't know how the hill, varies, it curves back and forth. You just want to walk downhill, and that's what the photon is doing. It's not. It does not know much about the kind of the global picture of the system. It just follows the path along the local curvature of the space-time, local fabric. So that's what is happening to a photon. And also other massive particles, they follow the fabric in a slightly different way, but basically following the same track. And does energy, yeah, so does energy get pulled by gravity? So energy means mass, right? So any mass, including photons, there's energy. So equivalently, there's also mass. So anything that is moving along this fabric, it will be changed. Its motion will be changed by the curvature of this fabric. So that's kind of the universal theory of Einstein that predicts the motion of all the things that would be doing near a black hole. Yeah, so that's what.
Great response. Thanks, Wenbin. Let's see. When it comes to the unknown universe, which is, so this is, you know, on a different tangent than what we've been discussing so far. When it comes to the known and unknown universe, Arif Ullah asks, we know that the unknown universe makes up 95% of the mass or energy. This all gets quoted in articles and such. That normal material only makes up 5% of the mass and energy density of the universe. How do we know if it's the unknown universe that's the other 95%? It's unknown. How do we know that that's what it is? How do we know that that's what makes it up? And how do we know that we only, normal matter, you know, protons and electrons that we're all made of, only make up roughly 5%? I can speak to this, but I wanted to see if other people wanted to chime in too. Nobody else? You guys are pointing at arrows, but I can't tell if it's at me or if it's at everyone, because we all.
You go first, Cameron.
Oh.
You go first, Cameron.
Okay. So that's an excellent question. An excellent question. Usually the breakdown is that, yeah, baryonic material, protons, electrons, the kind of matter that we are composed of and that we have an intuition about, that's only like 5-ish% of the total mass or energy budget for the entire universe. And then the next larger thing is dark matter, so which is a massive component. We don't fully understand what it is, but we know that it generally interacts gravitationally with other matter, but not through electromagnetic or nuclear forces. And we think that's on the order of like 25% of the energy or mass budget of the universe. And then the rest, the other like 70 or so percent, is like dark energy. And that one we have even less of a clue what the heck is going on. But the reason we get these relative numbers, first of all, it basically all stems from the cosmological models that we have to describe the behavior of the universe as we have so far seen about it. So right now, the common model that most of us agree fits the data the best. That's not to say it's perfectly spot on, and it may need a little bit of tweaking here or there to make it better. But the one that best fits is called it's called lambda CDM, which is kind of a weird term. But the CDM stands for cold dark matter. So that's the behavior of dark matter that we find that there's a need for explaining the universe around us, for there to be some sort of unseen gravitational component that we refer to as dark matter. And when people say that it's cold, it's not like, oh, ooh, that's so cold. It's more that it's cold in that dynamically it's not moving around really quickly, which is what hot stuff does. Like if you think of a hot gas on a microscopic level, it's hot because the atoms in that gas are moving around really, really quickly. Whereas if it's cold, like a cold gas, the atoms are moving really, really slowly. So cold dark matter is saying that the dark matter component, the dark matter particles, are moving slowly relative to each other instead of fast. So it's not that they're cold, because that doesn't really mean anything for dark matter. And then the lambda part of lambda CDM refers to the cosmological constant, which is essentially a shorthand for the dark energy part of this whole thing. And the dark energy part of this whole thing refers to, this is all within the idea that the universe started in a big bang and it's expanding outward. That's part of the cold dark matter model. But the lambda part is that it's actually accelerating in its expansion. It's starting in the recent epoch of the universe. It's actually not just expanding, but it's like speeding up in its expansion. And that's part of the kind of mystery that we're trying to understand about why dark energy exists and how it behaves, and really understanding a lot more than we do about it. So according to this model, you can make predictions to what the overall mass density is that brings us to the universe in which we live. And that's what describes, 70% of your energy should be in this component that's causing the acceleration of the expansion, and 25% of the overall budget of stuff should be in the dark matter that's causing things to clump into galaxies or into clusters of galaxies or even into clusters of stars. And then the rest is just, you know, the protons and the electrons and the atoms and the things that we have intuition for. Sorry, that was a long-winded thing, and I'm not sure I fully got it. But
so can I try to see if I
Absolutely.
understand on behalf of the audience? So I think what you're saying is, if you look at the energy budget, we need 3 times as much energy as anything else that we see to be pushing everything that we see faster and faster away from us. And we need about 1/4 of the energy that we can see to be moving everything around relative to each other in the galaxies and clusters of stars and stuff. That's where we get the numbers from. If you just add up all of the energy and protons and baryons and stuff, and then add up the energy it takes to move them all around, and then add up the energy it takes to push them far and far and faster away, that adds up to 100%.
that is a much more intuitive way of explaining that than I did. That's very good. Anything to add, other panelists?
Yeah, just that, like, although the 25% is also part of this unknown component, dark matter still, there are strong observational constraints. So although we don't know its true nature, its composition, we do know, like, we have very good observational evidence that it exists and how much of it needs to be present to explain the phenomena that we see.
I feel like we know a lot about what it's not.
Yeah.
We've like tried a whole bunch of things that it could be, and it's not that yet. It's like, there needs to be something. We just haven't worked out what it is yet.
Yeah, like, I think the way that was just the actual matter part of the energy budget is well constrained is a combination of, like, us observing the CMB spectrum and fitting the lambda CDM model to it, and the actual observational constraints we have that we can actually measure how much visible matter it is and how that scales to the dark matter. Like, we can visibly see that, like, the mass to light ratios of many of the bright galaxies are of order of hundreds of times greater than the actual visible light that we see. We see that objects orbit around the centers of galaxies, like, much faster than they should be because there's more matter than what we visibly see sitting there, and we can measure that, and we can see how that dark component scales with the visible component. And that's how we're able to constrain the within that 25%, that sub breakdown.
Great. There is a question about that Julius Reyes asks, is it possible to really look into what's happening inside of a black hole?
Yes, the answer is yes. For a very, very short period of time, if you want to sacrifice, you know, you can go look, but you can never tell anybody else what you have seen. So right there is an event horizon. You can drive your spacecraft into it, and it takes a finite, very, very short amount of time, roughly, you know, for a solar mass black hole takes about less than a millisecond for you to actually get crushed onto the point of mass that it has very, very high, very, very strong gravity that you're crushed and you're destroyed. For less than a millisecond, you're able to see what's happening inside a black hole. That's it. That's all. You're not able to tell anybody what you saw because no light. Even if you want to try to emit light, try to send signal, radio signal, visible light signal to other people to tell other people what you have saw, the light that you're sending out actually bends backwards because the gravitational pull of the black hole is so strong. The curvature of the space-time is so strong that the light you send bends back to the black hole, to the center of mass again. So you and the signal you sent both crushed onto the black hole pretty much at the same time. So yeah, you could, but nobody wants to do that. You can look at the black hole from far away, right? You don't need to go inside. There's no need to go there.
So Interstellar, the film where, I hope I'm not giving spoilers about talking about the end of that film, but it has been out for like almost a decade, maybe 5 years. Yeah, I never really fully understood. We should have Kip on here and explain the ending of Interstellar, where Matthew McConaughey's character essentially falls into a black hole and then it's a tesseract and is communicating with stuff. But what you're saying, Wenbin, is if you go in, you can check out what's going on there. You can figure out if it's a tesseract, but there's no coming back, and there's no way to shout back on your way in. It's all stars or whatever it is that's inside of there.
I'm pretty sure if you get stuck in a black hole, you're supposed to shout out Murph, Murph, Murph over and over again. That's what the movie taught me.
That's fair. That's fair. Let's see. Do black holes need matter to survive? It's almost an existential question, really. Do any of us need matter to survive? Nikita, Wenbin, what do you think?
I'll let the theorist answer first.
Yeah, so black holes, they can, apart from the tiniest black hole, which would evaporate according to Stephen Hawking, the massive black holes, they don't need you. They don't need matter. They don't need anything else. They can survive. They can stay there forever, for as long, much longer than the universe, the age of the universe. They can survive. Anything that gets nearby gets, swallowed. Even if there's no matter around, they don't need any other energy to support it, because they're by definition, there is no energy support inside the black hole. Everything collapses to the center of the black hole. So my answer is that they will survive. They're happily surviving in the universe. There are plenty of black holes that are happily surviving, starving. You could say that they're being starving, but they are still surviving. No problem.
Yeah, I think it depends on what your definition of what you mean by survive. Do you mean that by survive, it means that it just exists without emitting or without any radiation being produced that we can see? Or you mean surviving in the sense that it's just existing, like Wenbin pointed out? Because of course, black holes, they're not like other objects in our universe that the reason why they maintain a state of equilibrium is because there's gravity being balanced by some other force keeping that object together, whereas black holes are essentially a void in space-time where it's just gravity. That's all there is. And anything that approaches it that gets past the event horizon just falls in. So if you talk about survival in the sense of the black hole emitting radiation that we can see, then yes, there would need to be some matter lying around that the black hole eats off of for radiation to be produced and that we can detect. But a black hole just sitting there will continue to sit there, and it will take a very, very long time for it to evaporate away.
Indeed. Great. So a few questions from Julia Miguel Bernardes. One is kind of a semantic question that I think is worth addressing, and that is, can we use the word hypothesis instead of model, or can we make clear when something is a hypothesis versus a theory, because these are different terms that get thrown around and mean something in scientific speak that get used slightly differently in day-to-day speak. When you say, I have a theory that the mailman is stealing my mail, or something like that. It might just be a hypothesis. You don't necessarily have proof of it. Whereas in the field of science, we talk about the theory of evolution or the theory of relativity, and these have significant pieces of evidence for them. That's not to say they're perfect, but it's not you just hypothesizing something errantly without a significant amount. But I think this is a good point, and we need to be careful, not you guys, but like me really need to be careful about saying hypothesis versus model. Usually model, there's a little bit more to it, because usually with a model, you have to have, models I think are oftentimes synonymous with simulation. So you've coded something up, so you've really shown that the physics works, but it's not just something you are just like, I wonder if that's the case. There's a little bit more thought that goes into it. But do you guys have anything to add on that? No. Okay.
Yeah, usually when we refer to model, it's like usually we are, you know, like observational data is in the picture and we're fitting a model to the data, whereas a theory or a hypothesis may not necessarily be something that can observationally be verified. Like string theory is a theory and it's hard to like develop like a methodology to really confirm it's true.
Yeah, I would say it should be called the string hypothesis.
The string hypothesis. Ooh, I like.
But I don't know, Wenbin, like you're the theorist. Like, what's the lingo you use every day?
Yeah, there is a slight this is just my personal opinion. So there is a slight difference between hypothesis and theory, right? So Einstein's theory of general relativity was developed. There's a lot of math that Einstein did in a pencil and paper calculation for maybe weeks and months calculation. That is the calculation based on two hypotheses that Einstein posted. So that it's a part of his theory. So if you believe these two hypotheses, then here's the entire theory. Here's like a book, right? If you based on these two hypotheses, that you can have the entire theory, lots of predictions, right? Later on, you can test these predictions, observable predictions, and if there's anything wrong, if the theory does not agree with the observations, then either the hypothesis is wrong or the derivation. After the hypothesis, the derivation or your logic is incorrect, right? So right now, I think two of Einstein's hypotheses are correct. So that is a kind of a technical term. So one of them is the equivalence principle. So the equivalence principle is that no matter where you stand in the universe or near a black hole, on Earth, anywhere else, you only feel the local space-time, like what we mentioned earlier. You only feel like however a photon is gonna move, however an atom is gonna move, it only follows the local space-time. So it does not care how this curvature of the space-time is generated. It only cares about the local. So anywhere local. That's the first hypothesis. It only cares about the local space-time property, and locally, it's a very, very tiny portion of the local space-time is flat. So that's the first one, hypothesis one. The second hypothesis is the speed of light is the same in all frames. No matter where you're measuring speed of light in a flying plane or near a black hole or anywhere else in the universe, it's the same as long as you measure it in a small enough local. So those are the two hypotheses. And later on, people tested the kind of the theory prediction. There are many predictions that Einstein made based on these two hypotheses, and I don't want to say most of them, but near all of those predictions, whenever we can test them, we tried and they are correct. So it looks like to me that those two hypotheses are well posted. They're most likely correct. They're most likely kind of the guiding principles of the universe. Although we can never say 100%, that's absolutely true, because we haven't tested exactly every single exact accuracy that the theory predicts. But we're already pushing it. We're using our instruments to push every single predictive ideas, and they are correct to the limits that we can tell.
Yeah, like the scientific method is like the hypothesis is like synonymous to the initial idea. And then the theory is actually a formalism that is implemented based off of that hypothesis, which you would hope a strong theory will lead to testable predictions. And that's kind of the idea of the scientific method.
I think that's a really good, concise explanation for that whole question, response to that whole question. Thank you, guys. Okay, how about this one? What upcoming instruments and satellites are each of the panelists most excited about? Obviously, we have a lot of different focuses in our research. Some black hole people, both observers and theorists. I'm a weirdo who does like galaxies and stuff, and then Jesse, the realm of exoplanets. So what are you guys most excited about that's coming online?
AWST. It just has to launch at this point. Like, I'm not
Hopefully.
even an infrared person, but like after like, you know, decade of waiting for it,
Absolutely.
it just has to launch.
So people know, the James Webb Space Telescope, also called JWST, probably most of you know, but this is kind of seen as the successor to the Hubble Space Telescope. It's a bigger, the Hubble Space Telescope, the primary mirror is about 2.5 meters. What is that? Like this, 2.5 meters across. The James Webb is like 6.5. I think, is it 6.5? 6.5 meters. So really big.
It's going to take a month to unfold in space. That's the
Was that really
scariest
true?
part.
I didn't realize that.
Yeah. It's just terrifyingly large number of moving parts on this thing.
It's going to be a very tense month.
It was
Yes.
supposed to, you know, the original plan was it was supposed to launch like literally
A long time ago.
or something like that. And it keeps getting pushed back and going over budget. So astronomers have been like, we gotta wait for this thing. But it finally looks like
Halloween.
October, I believe.
Halloween.
Yeah. October is the launch date. And it's gonna, you know, when it gets up there, it's gonna be able to do some pretty sweet stuff. It's primarily operating in the infrared as opposed to the visible wavelengths of light. So there are good reasons for that. It'll be able to see farther away more effectively, and be able to penetrate some of the intervening dust and such. But yeah, you'll be able to.
So for exoplanets, yeah, so James Webb is going to be amazing for exoplanets because we're very lucky sometimes, and planets pass between us and the star. So if a planet is orbiting a star and it's lined up just right from our point of view, it actually passes in front of the star. And what happens is the starlight goes through the planet's atmosphere, and the molecules in that atmosphere will absorb light at different wavelengths and transmit light at different wavelengths. So the atmosphere leaves a fingerprint on the starlight, and James Webb will be able to like watch these stars as the planets go in front and go off, and be able to measure their atmospheres to find out what the composition of their atmospheres are. So we already do this with Hubble, but as Cameron said, Webb is, you know, 3 times bigger. It's so exciting, which means almost 10 times bigger in collecting area. And so we're actually going to be able to start looking at these super Earths that I mentioned, these new mystery objects that we don't really know much about. Like, are they cloudy? Are they clear atmospheres? Do they have big atmospheres? Do they have no atmospheres? Are they just big rocks? So James Webb is going to help us like start addressing this mystery of like, what are super Earths?
Any other instruments coming online aside from James Webb that you guys are excited about?
So I personally am mostly excited about gravitational wave emission in the future. So you guys already know that there's LIGO, which is a laser interferometer gravitational wave observatory, which is already running on. It has already gone through 3 operational rounds, 01, 02, and 03. And 04 is going to start June next year, which will be more sensitive than previous 3 operations. So LIGO stuff, as you saw, they have discovered many black holes and many neutron stars colliding with each other as well. So in looking into the future, I'm more excited about LISA, which is a very cool concept that you have lasers in space. You have 3 different stations, which are kind of the size of the Earth orbit around the sun, but the 3 stations are moving against with each other, but they shoot lasers to the laser point connects each of the 3 stations, and you can measure the distance between either two of the stations to the extreme accuracy, such that they can see supermassive black hole. They can see very massive black holes merging. They can see the small stellar mass black hole merging before, like decades before they actually merge. And they can see binary neutron star systems kind of also decades before they merge. We will get a spectrum of black holes and neutron stars much more in detail than the LIGO only see the last moment, like the last second of the entire history of the in-spiral dance and all the way. LIGO only see a final snapshot, whereas LISA, this space mission, is gonna see a history. It's like a decade-long history emerge. So I'm super excited about that. So we can actually know how these binaries form. Instead of only see the final snapshot, we see the history. So you can know how do they form in the history.
Knowing that astronomers like acronyms, does LISA just stand for lasers in space?
Laser interferometry space.
Array?
What is
Array?
Array, I think it's array, yes.
I'm going to call it lasers in space from now on.
Lasers in space.
Yes.
When is it supposed to launch? Like 10, 15 years?
So it was supposed, I don't know, I think in 10 years ago, it was supposed to launch in 2034. I think right now there is no like launching date yet. It may not launch in the 2030s. It's unclear when exactly it's gonna launch. It's been pushed back like GWST, but yeah, I don't know. I hope it launches within 2030s, 2040s.
Nikita, what instrument are you looking forward to aside from James Webb?
Well, it's always nice to see next generation X-ray satellites be launched. So, I mean, I'm quite, I have my own personal nepotism in that I really love the space telescope that I use a lot, NuSTAR, because it really is kind of unique in that it was the first focusing high energy X-ray telescope to be put into orbit. And that really opened up a lot of new science that we just couldn't have access to before because we couldn't see like all these objects that emit in the X-rays at very high energies. We couldn't get a spectrum, like a good quality spectrum at the very high energies because the focusing optics at those high energies didn't exist. So I thought NuSTAR was really revolutionary. And so I am excited to see more concept missions that are focused on bringing out next generation high energy X-ray telescopes into orbit. So eROSITA is kind of the closest thing apart from NuSTAR that we have right now. But it is like half controlled by Europe and half by Russia. So it's not like publicly available data. So I'm kind of looking forward to, there's a bunch of concept X-ray missions that are in development that want to essentially develop high energy X-ray telescopes to be launched in space. So I'm looking forward to that. So probably like to give you a specific name, like I'm excited about, you know, next generation telescopes like Athena and Prism and many more.
Yeah. I saw some presentations on those recently. They look super cool. My latest obsession with instruments is something called, well, there's a couple of different suggested proposals. It's not yet funded fully, but it's to build a radio telescope on the far side of the moon, which sounds pretty awesome. And we're actually to point out, in a month, we're going to have an astronomy on tap. No, in 3 weeks, we're going to have an astronomy on tap by one of the people who's behind one of these ideas called the LCRT, the Lunar Crater Radio Telescope, which is this proposed mission to go up to the moon on the far side of the moon. So you're blocked by the mass of the moon from all the radio interference that's coming from the Earth. Because the radio, you know, all of our electronics are putting out radio interference, which is a lot like light pollution in the radio part of the spectrum. And so by sitting over there, you get blocked from all that. So you have this like pristine location to observe the sky. But what's so cool about it is it gives us a whole new view. You know, people use this a lot, but this is true. It gives us a whole new window on the universe in the same way that gravitational waves gives us a whole new view on the universe, because when we're on the surface of the Earth, we can't, our atmosphere, the upper part of the atmosphere that's charged, called the ionosphere, blocks us from being able to see radio waves lower than a certain wavelength. Or no, I'm sorry, higher than a certain wavelength, lower than a certain energy. And when you're on the moon, you don't have that atmosphere, so you can observe these things. And it turns out one of the things that you can observe is cold gas that's going to form into stars before there are any stars that are formed in what's called the cosmic dark ages. So this is after the Big Bang. Things are expanding outwards, stuff starts to collapse, but we haven't yet had enough gravitational collapse to form stars and start pumping out light from the visible part of the spectrum that we could actually see stuff. So you have to rely on this. It's called 21 centimeter radiation, and it probes cold gas that's going to form into stars. And it's essentially like the only thing that we can possibly see from this era, and it'll be able to see that stuff. So I'm super, super psyched about that, but that's a long ways off. That hasn't, you know, we have to go to the moon again, and we have to install this thing, and it's going to be a thing. But anyway, check back in a few weeks and we'll have an Astronomy on Tap talk by one of the proponents of one of these with more details. So anyway, okay, only a few minutes left, still lots of good questions. Oh, and a quick response. How will that data get conveyed to the Earth? That is an excellent question. Essentially, you have to set up some orbiters that are relaying that data back to us as they orbit around the moon. Much like the deep space network that we have right now, that's able to communicate with the various different probes, like the Voyager probes and whatnot that are going into the outer solar system. That stuff contacts various systems on the surface of the Earth, but you'd have to have like an orbiter around the moon to be able to relay it back, to echo it back. But let's see, there was this question. I like this question. Do the scientists on today's discussion have a favorite black hole feature film? From Stephen Schreier. What do you guys think? What's your favorite black hole? I can tell you my least favorite black hole feature film. Well, no, I don't know. There's a few. The Black Hole, Disney's The Black Hole from like 1976 is weird. You wouldn't think that it's a Disney film, but that's not very good. Event Horizon, that's scary. Have you guys seen Event Horizon? You don't. Oh, it's scary. People use a black hole to power a spaceship, and then it makes everybody go crazy, and then there's like murders. It's like a horror film. It's really frightening. I saw it. It came out in like 2000 or 97. Yikes. But anyway, what do you guys think? Good black hole films, bad black hole films?
I mean, we're all affiliated with Caltech. I think we're contractually obliged to say Interstellar.
That's true.
Like, honestly, I'm not a sci-fi person at all. Like, I haven't even seen Star Wars. I'm not into sci-fi.
Oh, no Star Wars. Wow.
No.
Pick her off.
Blasphemy, I know.
Turn off her camera. She's done.
But, like, yeah, the only proper kind of black hole film I've even seen is Interstellar. And to be honest, it's pretty good. But I didn't like it because of the black hole physics. I liked it because, I don't know, it's a very touching storyline, and Christopher Nolan just has this way of directing films that, yeah, just has an amazing soundtrack. And
music's so good. I love the music to that.
It's just, yeah, I connected more with the emotional aspects of that film, but I did think that the graphics were very well done, and I definitely have to applaud that. So.
Okay, I have an update to my answer. Speaking of good graphics, there was a movie that came out called The Voyage of Time, which is actually a documentary narrated by Brad Pitt. And I have to say that one because my husband's animations were used in the film. So we got to go to like a red carpet event down at the California Space Center for the premiere of the film and stuff. And that one had black holes in it. So I have to say that one.
Did you get to explain black holes to Brad Pitt? Was he there?
Oh, so he actually, this is a whole thing. That was like 2 days after that he split up with Angelina Jolie. So he was doing like no public appearances or anything. And it was like, oh, well, you know, that sucks for you. Obviously, that's a big life thing that's happening. But also we were really excited for you to be, we never get to meet movie stars. So yeah, about equal, the tragedy of his, you know, life falling apart and us not getting to meet him.
Not getting to meet him. Yeah, that is a
but someone else like Rachel McAdams like slipped in the back after we were already seated, and we found out later, and it was like, well, we were feet away from Rachel McAdams. That was as exciting as it got.
Oh yeah, I remember one other space film that I saw and liked, Contact.
Yes.
That was actually also very well done in terms of like the radio astronomy and everything. And
yeah,
and
Jodie featuring the black hole and the wormhole that she travels through. Again, sorry, spoilers. It's been out for 25 years. I think it's okay to reveal that there's a black hole and a wormhole involved in that. But yeah, I mean, Interstellar, you know, written and scientific advisor, Nobel laureate Kip Thorne. Contact, written and scientific advisor Carl Sagan. So it's good to have these people involved with films to make sure that they're accurate. Wenbin, any highlights for you?
Yeah, I saw a movie. So I don't remember the name of the movie. So it was based on a book. The book was written by, so I graduated from University of Texas at Austin. So one of the professors there, Craig Wheeler, who wrote a book. Actually, I think his son filmed that movie. So the movie was, I don't remember the name. So the movie was, so Craig, who was the like kind of the major actor in the movie, he was a crazy physicist. So he works in a lab. So the lab does nothing, just adding mass, and so makes a very dense objects in the lab. So he accidentally made a black hole in the lab, which is kind of the mountain mass black hole, which does not evaporate very quickly. So the black hole basically is going through the Earth. So basically penetrates through the Earth, and it hurts some of the animals. If it goes through an animal, the animal gets killed, or then goes through a tree, the tree gets punched a hole. So it's a very tiny black hole, very tiny black hole. So the black hole basically goes through the Earth, and after some time it goes back. After some time, it goes back again. So it's like it's going through the Earth. So the Earth, yeah, exactly. So I was amazed by that. And an astrophysicist who actually noticed the pattern of this going through, found the period, and calculated the height of the black hole going.
Cliffhanger. He lost his hand to a black hole. Oh my God. Oh, well.
That was the last time it came through. It came through and took out Wenbin.
Right. Oh, you froze there. We thought you got consumed by a black hole, Wenbin. Sorry about that.
I'm curious whether you were amazed by this movie because of its very high production values, or its, fidelity to the science, or the audacity of the concept.
So the movie was never published. It was only just filmed by the professor's son. So it was only shown to the graduate students at UT Austin. So no, I don't think anybody else has seen this movie. So I was really happy. Like,
Cameron, you have to get this movie.
Yeah.
Yeah, I think we're gonna have to have a feature showing on a future stargazing lecture, so everyone can see the beauty of. So yeah, find out the name and give me some context. I'm gonna investigate this. We could be his premiere site with a whole 100 people viewing it. I'm sure rivaling any movie theater. Okay, we only have a couple minutes left. I'm just gonna ask one more reasonably, thematic question with everything that was discussed tonight, and that is. Sizes of black holes. We've talked about that in your presentation, Wenbin, you were talking about, there's the singularity in the center of the black hole, and then there's the event horizon. And most of the time we refer to things in terms of mass, right? This is a stellar mass black hole. So or a solar mass black hole, or it's a supermassive black hole. But what are the relative sizes of the actual event horizon, the area, once you pass that boundary, it's It's no more going back. Nothing's getting back out. So for like a sun mass black hole, what's the approximate size of the event horizon? Or the supermassive black hole at the center of our, I guess we had those images. That was like 0.01 light years across. So like 3 light days across. So like bigger than the solar system, but that's not very big in terms of astronomical sizes. But what about like a sun mass black hole?
Yeah, a solar mass black hole is very, very small. I mean, not like this you can hold in your hand. An Earth mass black hole you can hold in your hand, but you'll lose your hand immediately because it swallow your hand. So a solar mass black hole is much larger than that. It's larger. It's about 3 kilometers in size. So it's kind of the size of a very small town. So and it's extremely dense. It has so much mass. The space-time is so much curved. So if you put it on the the tongue will immediately get swallowed. Yes, yeah. They're very dangerous things to play with.
Very dangerous indeed. All right. Well, there are still like literally 30 questions that we didn't get to. I'm sorry, audience members. We tried to do our best. I'm sorry, panelists, that I couldn't delve out wonderful questions to all of you. But thank you. First of all, thank you, Wenbin. Excellent presentation. And thank you to Nikita and Jesse. Great job on the panel answering questions. It was a pleasure to have you guys here. And our audience, thanks for joining us tonight, spending your Friday evening listening to us yammer about on scientific topics. It's a pleasure to chat with you guys. Again, these events happen once a month. Our next one, I forget, I don't yet have a topic for it. Probably on neutron stars, which is another related massive kind of object, not quite as massive or as bound as a black hole, but still pretty interesting. And then our sister series of events, Astronomy on Tap, are happening. Our next one is a week and a half from now, all about the first stars and the first galaxies in the universe. And then the next one after that is 2 weeks, and that'll be about Sophia, as well as this lunar crater radio telescope that I'm so excited about. So yeah, thanks for joining us, and we will see you next month. Have a good night, everyone. Stay safe.